Your ESP32 drone can actually fly with a real hobby-grade radio controller. With the ESP32 as a flight controller configured in Betaflight, you save money, unlock way better range than Wi-Fi or Bluetooth ever will, and get real hobby-grade control using your favorite RC transmitter. Radiomaster, Express LRS, FlySky, FrSky, Jumper, you name it. In this guide, you'll learn how to set up different receivers, motors, flight modes like Angle and Acro, PID Tuning, rates, blackbox logging, and a ton of in-depth settings on something so tiny and affordable. So here's what you need to get started. For hardware, you'll need to build an ESP32 based quadcopter like my ESP-FLY micro drone seen in my previous video. The compatible motor driving methods you have is either a MOSFET driver for brushed motors or ESCs if you're running brushless. For control, you have two options. You can either build an ESP-TX link that sits in your controller's JR bay using a second ESP32 for ESP-NOW communication between your radio and the drone, or you can simply connect the receiver to the drone that speaks a supported protocol like PPM, SBus, iBus, or Crossfire like the ELRS EP1 I'm using. And for the drone's actual flight controller, you can use an ESP32 or ESP32S3 paired with an MPU6050 or MPU9250 IMU for stabilization. Now here's where everything comes together. Once you start wiring the microcontroller unit, the gyro, the motor drivers or ESCs, it becomes very clear why a custom PCB makes the whole assembly much more solid and professional. Like my ESP-FLY's thumb-sized 3-in-1 flight controller stack with the Xiao ESP32S3 as the brain, the MPU6050 gyro, and a 4-channel brushed motor driver all built in. Whether you use my PCB design or create your own, getting it manufactured is very straightforward. For mine, I uploaded the Gerber file to JLC PCB, chose the basics, number of layers, quantity, thickness, and the color, and I got an instant quote. And if soldering tiny SMD parts by hand just isn't your thing, you can enable their PCB assembly service. Upload your bill of materials and pick and place file, and they'll handle the components for you. My boards were $2 before shipping, produced in a day or two, and delivered almost as fast as an Amazon order. New users also get $70 in coupons, making it one of the easiest, most affordable, and most reliable ways to build a clean flight controller for your drone. The link is in the description to sign up to JLC PCB and order the board. To get the quadcopter's firmware, I've left a link to ESP-FC by RT Lopez on GitHub, a Betaflight compatible software for ESP32 flight controllers. You'll want to scroll down to the flashing section and click on the releases page. Under the latest release, download the firmware binary file for your ESP32 board and extract the zip file to end up with the binary. If you've never uploaded code to an Arduino or ESP32 before, you may need to check you have the CH340 driver installed on your computer prior to the next step. But if you have before, then you can skip installing it. Now you'll want to head to Espressif's online flasher for ESP chips. Plug your drone into your computer and hit the connect button. But hang on, if you get this error, copy the site link and paste it into Google Chrome, a browser that can access serial ports. Check you have the right baud rate, click the button, and select your ESP's COM port in this pop-up window, and then hit connect. Based on the output, check it has detected your chip. Set the flashing address to 0x00, select the firmware file you downloaded, and hit program. After it has flashed successfully to the board with the following output, you'll want to disconnect and reconnect it to power cycle it. Next, you'll want to install the 10.10 version of Betaflight Configurator on your computer. Hit the link in the repo, scroll down to the right version, click on it, scroll some more until the Assets section, and download the installer for your OS version. I'll skip the installation part, but once it's set up, Betaflight should appear like this. Open it, click on the Options panel, and check you've enabled Show All Serial Devices. Then you'll want to select your ESP's COM port up here and hit connect. If you get this warning, don't be alarmed. Close this window as things like the motors aren't set up yet. As expected, the 3D view won't move with your drone until you've set things up in the command line interface, or CLI for short. If you type the command get pin and hit enter on your keyboard, you'll see the current pinouts to each function based on your ESP. which is most likely not how you want it. So head to the repo, under Documentation, click on Setup Guide, Pinned Functions Reference, and you'll get the list of default assigned pins, which you can copy and paste in a text editor to modify, like I've done for the way my drone is wired. Ensure pin input RX is set to -1 as it's unused. Assign GPIO pins to motor outputs such as rear right output 0 to GPIO 4, front right output 1 to GPIO 7, rear left output 2 to GPIO 3, and front left output 3 to GPIO 1. The icon on the left simply shows the motor direction and order. If you build a drone with wiring that differs from my ESP-FLY, you'll most likely enter different pins according to your wiring. For alerts, set the pin your buzzer or LED is wired to right here. Check you've matched your board's serial UART pins as your computer and ESP communicate this way. These two are left unused, and the last two UART pins set up to take your external receiver if you choose that as your method of communication. Define your board's I2C pins for the gyro. Choose a pin for voltage monitoring, that's ADC 0, and a pin for current monitoring, which is ADC 1. It's completely optional, and I've set it to -1 as I'm not using it. Below you have SPI pins for other sensors which we won't be using. You can optionally set each to -1. The buzzer invert functionality allows you to make the buzzer or LED, in my case, to be normally on or normally off when blinking, depending on whether you put a 1 or a 0. Now that you've defined your pins, copy this table and paste it in the CLI. Hit enter on your keyboard to set the pins, enter the commands save followed by reboot, and whatever you do, do not go to the other tabs from here or it'll erase all your configurations. Instead, hit disconnect, connect, and you should be able to see things like a 3D interpretation of your drone's orientation. If you don't, you may want to check the configuration tab, and if you get an error saying that your gyro was not found, simply disconnect your drone safely and reconnect it. But if you still don't see your gyro being detected, you may need to swap the I2C pins in the CLI. Once detected, move back into the configuration tab and set up the gyro. Set the PID loop frequency to 2 kHz, ensure the accelerometer is turned on. Feel free to align your gyro by a few degrees if it doesn't sit perfectly level when flat. Set the gyro orientation here by the right amount of degrees if your gyro isn't pointing the right way according to the 3D interpretation. Down here, you can give your aircraft its name, scroll down a bit and keep dynamic filter on, and only enable soft serial if you plan on configuring your quad over Wi-Fi, which I won't be doing. Instructions on that can be found in the GitHub repository. In the beeper config section, it's up to you on what functionalities and when you want your buzzer or LED to activate as an alert. Once you're done in the configuration tab, click the save and reboot button and reconnect. If you go to the Sensors tab, you can tell whether your gyro for orientation and accelerometer for changes in velocity are both working properly. Going back to the Setup tab, let's calibrate the accelerometer with the button up top. When calibrating, check your quad is either laying flat or held perfectly level and still. For these next steps, you'll need to plug in your drone's battery. I'm using a 250 mAh 1-cell LiPo. Navigate to the Power and Battery tab. To see a battery voltage reading as such at the top and receive battery warnings, select the following. Onboard ADC set as the voltage meter source, 3.4 as the minimum voltage, 4.2 as the maximum, and 3.5 as the warning voltage. If you're not measuring the current drawn, keep this box set to none. In the voltage meter section, set the divider value to 5, and it should be set after you hit save and reboot. Now head to the Motors tab. The only multi-rotor the firmware supports is a quadcopter, so keep it set to Quad X. Motor direction cannot be reversed in the software, so the only way to change the direction is by swapping the motor wires. With the quad pointing up or forward, this is the correct direction each motor shall rotate. And here's the pinout as a reminder to know which motor corresponds to which pin. If, for example, you were to enter pins in the wrong order, your drone would literally go ballistic. but when the pins are entered correctly, corresponding to the right motor, the drone takes off how it should. In this drop down here, select the ESC protocol for the type of motors you're using, as the software's PWM protocol is not recommended for quads. Brushed would be the one to use, like in my case. Select a D-shot or one-shot protocol according to your ESC if you're running brushless motors. Set the maximum pulse width modulation frequency for driving the brushed motors, which is 8000 Hz. If you try to set it any higher, it'll reset back to this maximum. Before you test the motors, take the propellers off to prevent damages or injuries, then enable the slider confirming you accept the risk, and test each one at a time or all motors at once to ensure they're spinning in the right direction. Now let's get control of the quadcopter using the first method, which is through an external receiver. For mine, I'm using a Happy Model EP1 2.4 GHz Express LRS receiver, which uses two wires for communication via a serial port, a wire for powering it, and a wire for ground. You'll want to attach your receiver and trim its wires to the right lengths according to where it'll sit. Strip the wire ends and solder the receiver's RX wire to TX GPIO 8, TX to RX GPIO 9, power inputs to 3.3 volts, and ground to ground. If you're using a different ESP, the TX and RX pins on the board can be set to any other two GPIOs. For receivers on any of the other supported protocols, you'd use only one wire sending signals to a sole RX-defined pin on the ESP for one-way communication, whereas a Crossfire protocol receiver like the EP1 uses a second wire which allows it to work as a transceiver, sending telemetry data such as battery voltage back to the transmitter. As this feature is more like an extra, I'll leave it up to you to set up telemetry. But if you are going to hook up a one-wire protocol receiver like the FlySky IA6B on the iBus protocol, then you may want to refer to this wiring diagram I put together for you. The boost converter is used as the ESP32 cannot power the receiver alone with its 3.3 volts. And if you're using a 2S or higher battery, replace the boost converter for a linear voltage regulator. Now let's get the transmitter paired to the receiver. First, turn on your controller. I'm using the Radiomaster TX12, and check that the corresponding radio protocol is selected. Then, power on the drone, and you should see the signal bars appear, showing it has connected. If you have never binded before, you'll likely not see these, and you'll need to follow the binding instructions for your specific type of receiver, like the video I've linked at the top right for binding this transmitter to an ELRS receiver. Once successfully bound, connect to the drone in Betaflight, head to the Ports tab, and ensure you've enabled Serial RX for the UART port the receiver is using. Then head down to the Receiver tab, set the receiver mode to Serial via UART, and the serial receiver provider to Crossfire, CRSF, if you're using an ELRS receiver like mine. iBus if you're on FlySky, and SBus with signal inversion done for you if on FrSky. For channel mapping, set the correct letter order for your pitch, roll, yaw, and throttle channels according to how your receiver takes it. Mine had to be TAER1234 to have my gimbal movements all match to their designated functions. Afterward, click Save and Reboot, and all the channels should be set. Then you'll want to head to the Modes tab and add a range for the ARM function. You may select the aux channel manually, or if you don't know which is which, set it to Auto to detect your desired toggle switch for arming the quad as you flick it back and forth. Then move the slider to the right, and repeat this for the other modes you want to use, such as the two flight modes, Angle and Air mode, as well as the beeper. So when you flick each switch all the way, you should see a response with the corresponding cursor falling into the respective range. Unplugging the quad, let's give it a quick flight test on the ELRS protocol. That was a successful flight on the Express LRS protocol. But if you want to fly your ESP drone as it is, using the built-in radio chip, then you'll want to set it up with the ESP-NOW protocol, which is just as responsive and has a range of about 200 meters. We'll disconnect the EP1 receiver and clip the antenna back onto the ESP32 board. To control the quad, let's make the transmitter link, which will sit in the controller's JR bay using another Xiao ESP32 S3 like the one in the drone. Any other ESP32 should work fine for this purpose. Following the wiring diagram on RT Lopez's TX repo, take a 5-slot female pin header row and solder a wire for ground, VBAT, and PPM signal in this exact arrangement. Then find an L7805, which is a 5-volt regulator, and from the connector, solder the loose end of the power wire to the input pin, the ground wire to ground, a new wire to extend ground, and another wire to the output pin of the LM7805. Connect this output to your board's 5-volt pad, ground to ground, and the signal wire to your chosen pin, which in my case is GPIO 4. Now the TX link is all wired up. To make it fit the enclosure, you may need to bend the connector pins and trim any unused pins. You may optionally clip on an external antenna if your ESP board supports it and your TX link is almost ready. Before shoving it into your controller's JR bay, we need to program it. Head to the ESP-NOW RC link repository I've linked below, also by RT Lopez. Originally, this firmware is set up to work on an ESP Room 32 board with the PPM pin programmed to GPIO 13, and it supports 8 channels of control. If you're using the same board as suggested, you'll need to head to the releases page and download the binary file for flashing to the ESP32 board. Unzip the file to reveal the actual binary, and you may need to rename it to avoid conflict with the flight controller's binary file. Then visit the ESP tool website and flash it the same way as you did with the flight controller. But if you're using an ESP board other than the default ESP32, go to the repo and download the zip file for the project. When you open the main folder, head to SRC and open the TX file. You'll see where you need to change the PPM pin. Even though you can make the changes here, you'll still need to flash the firmware to the board. And to do that, open Visual Studio Code and the Platform I/O extension within the editor. If you don't have either, I've linked tutorials on how to install them in the top right corner of this video. For Platform I/O, you'd usually find it in the Extensions tab through a search and be able to install it from within the editor. To open the project, make sure you're in Platform I/O, click Pick a Folder, select it, and you should see it appear in the top left under the name ESP-NOW RC Link TX. Before proceeding, it's important the project's Platform I/O file opens up and is found in the folder. Then head to tx.cpp in the SRC folder, and on line 9, change PPM pin to 12, 3, 4, or whatever GPIO pin you've wired it to. Afterward, head to the Platform I/O file. This is where you define your ESP board with its platform, board, and framework. If you're using an ESP board other than the one I'm using, head to the Platform I/O tab under Boards, Search, and locate it. Copy these 3 lines as the board ID and paste them in a custom board section like I've done. Once that's set, compile it with the command pio run-e and your board name in that format. Type this line into the terminal and hit enter on your keyboard to compile the firmware. And once successful, upload it to your board with the command pio run-e, your board name, -t, upload, and it'll automatically find the COM port your board is connected to and flash to it. Now you can unplug the TX link from your computer and connect it to the 5-pin header row in your controller's JR bay. It's worth checking the pinout on your exact controller in case it differs from mine. So essentially, it gets powered from the battery's supply through the regulator, but only when the controller is configured for communicating with an external transmitter, which we'll set up now. So you may shut the cover while allowing the antenna to protrude, power on the controller,
Welcome to Edge TX,
and go into Model Select. Right now, it's using the internal ELRS transmitter module as you see, but in Model Select, you need to scroll down and create a new model, automatically selecting it. Then hit the Page button and use the scroller wheel to enter ESP-NOW as the name to identify the protocol. Hit the Return button, scroll down all the way to where it says External RF, and enable it to use PPM. Check the channels range from 1 through 8 and hit the Page button until you get to Mixes, where you'll set up the aux channels such as for arming the drone. Highlight the source selector, click it, and flick the toggle switch you want to use for arming, and select it. Then scroll down to Switch, flick the toggle switch to the armed position, and select it to have the mode activate at this point. Exit out with the Return button and confirm it highlights when the switch is fully up. Then you may repeat this for the other modes you like, such as beeper, angle mode, and air mode. Hit the Page button until you end up back at the models page and select ESP-NOW, the model we just finished setting up. Return back to the main screen and you should see it labeled as the one that is in use. Connect your drone back to Betaflight. In the Receiver tab, select Built-in RX as the receiver mode, NRF24 250K as the SPI bus receiver provider, and adjust the channel map to AETR1234 or the one that corresponds to your input. Then hit Save and Reboot. And again, check that each channel matches what it's supposed to do. But let's say you want to build a 100% ESP-NOW based controller for your drone like friends of mine, Raja and Nick Hill, did from the Connect Robo team. Then you may want to check out their GitHub repository for the code, parts list, and project instructions for their drone setup linked below. Back to the configurator, the Modes tab remains the same as with the ELRS setup. The Adjustments tab does nothing, and getting tuning presets for your quad won't work either, and it's not worth trying as these features aren't supported by the firmware yet. In the Failsafe tab, the only option is for the quad to drop in cases like the battery running out, cause if you try enabling something like land and save the changes, it'll default back to the drop procedure. Fortunately, Blackbox is supported for logging your flights. To enable it, select Onboard Flash as the logging device, 1 kHz as the logging rate, and choose your debug mode to track those specific metrics. Click Save and Reboot for the changes. Make a quick test flight. Reconnect your quad and click Save Flash to File to download the Blackbox logging file and play it back in something like the online Betaflight Blackbox Explorer. I've left a link below to visit it. Click on Open Log File to upload your file, and you should get an interface as such where you can select a specific log and play it back, logging data like motor speeds, stick positions, and the drone's orientation. Back in Betaflight, you can enable Blackbox Erase as a mode, and in the Configuration tab, enable the beeper to notify you of the erase when you flip the switch, or simply erase the flash in the Blackbox tab to reset it for your next logging session. And keep in mind you only get so much flash on an ESP32 to store such data. Now here comes the fun part, let's tune the quad. First, let's get it flying stable through adjusting trims for yaw, pitch, and roll. Flick the switch to enable angle mode, the self-leveling flight mode, power up your quad where it's nice and level, arm it, and take off. If you notice it drifting in one direction, press the relevant trim button on the controller in the opposite direction to correct it, and keep correcting it in angle mode until it can fly level. Great, now let's connect it back to Betaflight and tune the PIDs to achieve the desired stability. With default PIDs set, flying it feels like it's trying to compensate for a bigger quadcopter. It's a bit sluggish, and that doesn't feel stable. Let's fix that. But to give you a basic understanding of the effects in the drone from the changes in PIDs, Play around with P, or the corrective spring effect, on both pitch and roll. Lower it to about 10 and you'll see your drone behave like it wants to tip over. Not enough corrective force, preventing it from ever gaining stability. Now lift the P values to 100 and the drone is given enough correction, providing the stability required to fly. But know that anything higher may create overshoot. Now for the D values, also known as the term that provides damping and anticipates future error. Set both to 0 and you'll notice your drone oscillates a bit more frequently after quick movements. Set both Ds to 80 and you'll notice much smoother handling when flying side to side, but personally 20 works good, as when I move the sticks more aggressively, I can make the drone more snappy for sharper turns. Now for the I value, which acts like a memory of all errors to eliminate persistent issues, such as the drone drifting to a steady breeze or a weight imbalance. Lower it to 10, and you'll notice that it kinda has a hard time stabilizing after the series of rough movements. Lift both I values to 100 and you'll notice it compensates for the persistent back and forth movements I'm making by smoothing out the motion much quicker. But my preference is 45 for both the I values, as the perfect balance for my size drone to maneuver well. So these are the PID values I landed on for my 50mm quad, but yours may differ depending on the size and other aspects of your quad. If you want to learn about PIDs more in depth, watch this video I've linked at the top right corner. Switch to the Rate Profile Settings tab to tune the rates or the responsiveness of your drone. Keep in mind that adjusting them won't make a difference in responsiveness when the drone is in angle mode, only when you switch back to acro. Lowering all values on pitch and roll makes the quad nearly unresponsive. As you see, my dramatic stick movements barely make it go where I want it to. But if you raise the center sensitivity, rate, and the expo values high enough, you'll get the responsiveness you need. Higher values than usual are needed on a tinier quad like mine. Now, with these settings saved, it's a lot more stable and maneuverable as a micro ESP quad controlled with a proper radio controller. And in case you prefer following this tutorial in written format, I wrote you a blog taking you through every step with images and key tips to getting your Betaflight enabled ESP32 drone up and running with your radio controller. Find the blog posted on Elector Labs. The link is in the video description. Let's give it some more airtime to see what it's capable of now having this new firmware. Angle mode, exactly how you fly most toy drones. It's beginner friendly, and moving the pitch and roll stick makes it go the intended direction with angle limits, but what sets the mode apart is it uses not only the gyro, but also the accelerometer to self-level when you let go of the pitch and roll stick. Acro mode, short for acrobatic. It's how most FPV drone pilots fly their drones, allowing for complex maneuvers like flips and loops in midair. Using the gyro only, it gives you complete manual control with no angle limits by having the sticks control the rate of rotation rather than the angle of the drone. When the stick is moved and released, the drone continues to rotate at that constant rate until you correct it by moving the stick in the opposite direction. Air mode is actually a feature added on top of acro mode, helping maintain the quadcopter's stability and control during maneuvers, adjusting motor speeds even when the throttle is low. I find air mode makes doing flips much easier than on acro alone. You may not see it now, but you'll certainly feel the difference when trying to do flips. Even though I mentioned this already in the ESP-FLY's video, you guys keep asking me about the flight time on this drone, which is 5.5 minutes on a 250 mAh cell, and when the battery starts going low, it warns you via this blinking LED. And if ignored, it runs out eventually and drops like it's supposed to do according to the failsafe programming. The range used to be 50 meters on access point Wi-Fi controlled from my phone, and now goes up to roughly 200 meters from the transmitter via ESP-NOW. With the ELRS receiver, you may get several kilometers of range, but why so much for such a tiny drone? So I stick with the convenient ESP-NOW protocol using the built-in receiver the ESP32 already has. If you want to add an FPV camera with a VTX, keep in mind that for now, only the TBS Smart Audio protocol is supported for video transmitter control, and you'd need to set up a dedicated UART for it in the Ports tab. Once you do, then you should be able to configure the usual settings in the VTX tab. To have your on-screen display OSD overlay with flight info, keep in mind it's not implemented in the project, but you can use an external OSD module called the Minim OSD wired to the system, something along the lines of what's on this diagram, running a firmware called MWOSD, short for Multi-Wii OSD. If you're keen on implementing this, learn more about it reading the documentation I've linked below. To keep it simple, you can just use a basic camera plus VTX unit like this WTO5 5.8 GHz 3 gram all-in-one cam I've used for all my micro drones. To the ESP-FLY, it attaches using this cover mount and gets powered directly from the 3.7 volt battery. I show how to properly install it in the ESP-FLY tutorial video. You watch the feed as you fly from a 5.8 GHz FPV headset like my Fat Shark Scout. Pairing it is easy. Hold down on your headset's scan or auto search button to find the channel the camera is on, and its feed should appear on the display right away. Now, let's fly this micro drone in first-person view. And this is just the beginning. Upgrades like GPS, altitude hold, and more are on the way. So if you want to see future updates to ESP-FC by RT Lopez, the link is below to support him and grab the firmware. And if you want to build the micro drone I used in this video, go watch my ESP-FLY build guide video next. It walks you through the entire assembly step by step. Thanks for watching, and I'll see you in the next video. If you can imagine it, you can make it.